to talk about the roller coaster problem, or the loop, and kind of explain what's really going on here. So I have a question that says an engineer is designing a roller coaster with a vertical loop of radius 8.4 meters. Okay, before the loop, the engineer needs to determine what height the roller coaster must start from in order to safely make it around the loop. Okay, so the first thing I'm going to do is draw a picture. Okay, so maybe you could say this is your loop. Okay, this is your loop. Okay, this is our loop. I'm trying my best to make this as circle as possible. So maybe we could say this is our loop, okay? Now if this is our loop. Let's draw the free body diagram. Let's look at the object from the bottom. So you have a roller coaster, okay? So maybe we could call this is a roller coaster, and we're at the bottom here. And maybe there's just some person sitting inside, okay? So there's a roller coaster at the bottom. So what are the forces? Yeah, so this is my roller coaster. So what are my forces that are acting on the actual roller coaster at the bottom? Well, we always know gravity is pulling straight down. So we know this is mg. Yeah. We know this is gravity, the gravitational force, which is mg. Okay. Well, what's preventing the car from actually going straight down through that roller coaster? It's actually a normal force. So we know the normal force is actually equal and opposite, and that's canceling out gravity. And it's the reason why the cart is stationary at this point. Okay, so at the bottom we have the normal force, and we have gravity that's pulling it down. Now, what's interesting about this stuff? Well, what about the top? Well, if I move, you can imagine my wheels are now going to be upside down. And so if we look at the object at the top, there's the person. He's flying out, and that's nice to know. Hopefully, you land safely. Okay, and there's a person flying out. And so now what are my forces here? What are my forces at the top? Well, remember, we still have gravity that's pulling straight down. So maybe we could call this mg. Okay. Now we still have the normal force. Where did it go? It didn't disappear. But what direction is normal force pointing in? That's the point. That's the question. That's my question to you. So remember, as we're going in the circle, maybe you could call it a kissing circle. Yeah, as we're going in the circle, well, where's my velocity? Where's my velocity? Where's the cart? Where does the cart want to go? The cart actually want to go tangential to the motion. And so you could see that my velocity is tangential to the circle. And so this is my velocity. Okay, so and so there's my velocity. Okay, it's tangential to the circle. And so why did I tell you that? Because that is telling me that my cart at the top, at this point, my cart actually want to fly off the roller coaster going straight across, okay, tangential to the circle. And so in order for that not to happen, my normal force will actually be pulling down. And my normal force will actually be pulling down. Okay, and it's the normal force that is pulling down that is keeping the cart from actually flying off. Okay, the normal force is actually keeping the cart from flying off. And so that is a very important point to make. And so what if we wanted to draw the free body diagram for the cart at the top? This is interesting, right? The bottom is pretty straightforward. What if we wanted to draw the free body diagram for the cart at the top? Well, if I squish my object down to a dot, what are my forces that are acting up on it at the top? Okay, well, we always say gravity is pulling straight down, so maybe you could say this is F grav. Yeah, this is the force of gravity. But also, there's a normal force pulling down. Okay, and maybe you could say this is F normal. So there's my gravity, there's my normal force pulling it down. Okay, well, that's nice to know. And so those are the two forces that are there. So therefore, my F net, my net force at the top will actually be gravitational force plus the normal force. Okay, so that would be my F net. Okay, so that's pretty straightforward, and that's the idea that I want you guys to get. Now, my question to you is, what if I had a question that asked, well, what is the, maybe I should write it out. So maybe I wanted to know what is the minimum, speed required to safely make it around the loop. Okay, what if I had this question and I ask you, well, what is the minimum speed required to safely make it around the loop? Well, we got to think of a couple things here. As we're going around the loop, we know that the force towards the center, which is centripetal force, is really what we need to concern ourselves with. This is what we need to relate our velocity to. Okay, because we need to know what the velocity is related to the centripetal force in order for us to make it safely around the loop. And so we know the acceleration due to the centripetal force, and we'll just make this point clear. The centripetal force is actually not a real force. We just use that fancy word to say it's the force towards the center. Okay, so I just want to make that clear. Okay, so we know that acceleration due to the force of the center, that is equal to the velocity squared divided by r. Okay, now what's my acceleration force due to the center? Well, this is gravity, and so that's 9.8 meters per second squared. Okay, and we know that's equal to the velocity squared divided by r. Well, what's my r? In this problem, my r was 8.4 meters. It was given. And so I know that my velocity squared will be equal to 9.8 meters per second squared times 8.4 meters. Okay, and so my velocity will be equal to the square root of those two. So my velocity will be equal to the square root of 9.8 meters per second squared times 8.4 meters. Okay. And so if I plug that into my calculator, I get 9.07 meters per second. Okay. And so again, this is how we would know what the minimum speed we need to travel at in order for us to safely make it around the loop. Now, I might pose another question to you. Okay, the question I might have is also, well, what is the minimum height? What is the minimum height the roller coaster must start from in order to make it safely around the loop? Okay, so that would be my question. What is the minimum height the roller coaster must start from in order to make it around the loop? Well, for this one, we got to use the energy principle. We use the conservation of energy in particular. And so if I'm looking at this, we know the change in energy of the system is equal to Q plus the work external. Okay. Well, remember, there's no heat being trapped. There's no heat being transferred. So we know this is 0. Okay, and what's my work external? Well, the only thing that we could think of is gravity. Remember, we have no work when the force and the displacement is perpendicular. And so if I'm looking at this, the gravity is pulling straight down, but my force is actually my displacement. All right, the velocity, which is in the direction of displacement, is actually going perpendicular to that. And we know the work external is 0. Gravity does no work. Okay, so that being said, we know that the change in the energy of the system is equal to 0. So therefore, E initial must be equal to E final. Okay, and there's how we derive our conservation of energy. Now I want you to take a close look. Initially, we're at the bottom. Okay, initially we're not moving. So we have no kinetic energy. And so the only energy that's present is potential energy. And specifically, we have potential energy due to gravity. Okay, so that's our only initial energy. Now, what's our final energy while we're at the top? Well, you could see if we start off with potential energy, most of that is going to be transferred into kinetic energy. And so at final, we have some kinetic energy. So we have some kinetic energy. We have some kinetic energy final. Yeah, we have some kinetic energy final. But what about my potential energy? I also have potential energy. So I also have potential energy due to gravity. final. Now, some of you might be saying, what? But remember, at the top, we got to take into account the potential energy due to gravity. Hence the reason why we have this vector here. We have to, it did not go anywhere. We had to take into account the potential energy due to gravity. And so initially at the bottom, initially at the bottom of the roller coaster, initially at the bottom, we only have potential energy due to gravity, and we say this is just some sort of mgh. We're at a certain height. Okay, we're at a certain height, so that's just mgh. Well, what's our kinetic energy final at the top? Okay, we'll know this has to be 1/2 mass times the velocity squared plus, well, what's my potential energy due to gravity? We know it's mgh, but in this case, I want you to take a clear look. We know the radius of the circle is from the middle, so we could say this is a dot, and we'll say the radius is to any point. Okay, in this case, we're going to use it in vertical direction, so from here to here is the radius. But look, our height, we just traveled 2 times the radius. Okay, so you can see from here is 1r, and then from here to here is 2r. So that's a diameter of 2 times the radius, and so the height at the top is actually 2r. And so if we look at this, we could just simply plug in the height. And let's say this is mg height, and then we could rewrite this as mgh. Mgh initial plus 1/2 mass times velocity squared plus mg2r final. Okay, and now we set up our beautiful equation to just solve. Well, the good thing about this is that we're solving for the height, so we know that we're solving for h here. Okay, well, if we have mass on both sides of the equation, if we have a mass in any term, in every term, we could go ahead and cancel those. So this is 0, this is 0, and this is 0. And so we're left with gh is equal to 1/2 velocity squared plus g2r. Now, again, since I'm solving for height, I'm just going to go ahead and divide by gravity. And so if I divide by g on both sides, this will be divided by g, and this will be divided by g. The good thing about this is that this goes to 0. Yeah, for this one, I could factor out my 1/2 and just divide velocity squared by g. And so this goes away, this goes away. And so we get our height to be equal to 1/2 the velocity squared divided by g plus 2r. Yeah. So now this simply becomes plug and chug. Yeah. So we have 1/2. Yeah. So we have 1/2. Well, what's our velocity? We just found it. It was 9.8. It was 9.07. And so we have 1/2 9.07 squared. So we have 1/2 9.07 squared divided by 9. So we have the velocity squared divided by g. Okay, so we know g is 9.8. G is 9.8 meters per second. Okay, and we know this is 2 times the radius, which is 8.4. Yeah, and I'm just gonna leave out the units since we're doing a calculation. So if I plug all of this in, this now becomes, well, we know 2 times 8.4 is just 16.8 meters. If we divide this by, so let's plug in my calculator. 9.07 squared, 9.8. Yeah, I should get 4.535 meters. And if I add those up, I get 21.335 meters. Okay. So again, this is how we simply plug and chug.